final section for our probability packet, and we're talking about combinations today. So we're moving from permutations, where order matters, to combinations, where guess what? Order does not matter. So the best way to think about combinations, I think, is to think of when you get a combination burrito. And I think I already said this earlier, a week or so ago, but when you have a combination burrito, let's say you have 5 items that you include in that burrito. You have beans, rice, cheese, lettuce, tomatoes. Beans, rice, cheese, lettuce, tomatoes. That's 5, right? So does it really matter the order that you stick them in there? No. Could you actually put tomatoes and lettuce first? Yeah. Yes. It wouldn't change what the ingredients are in this combination burrito. So combination is how many different combinations could you make given a certain number of items. This really is fun to think about when you think about Subway. Because when you go to Subway, there are lots of possible sandwiches that could be made, right? And you have how many types of bread even?
Like 7.
Flat bread, whatever. You could even go without bread. They have salads now. You know, there's so many possibilities. Okay? This is an arrangement where order doesn't matter. Okay, very good. So the number of combinations is given to us in a formula like the permutation one. But what we're going to do is we're going to divide by something more. So in our permutations, we had the number of possible, what did we say? We have a certain number of items. So the total possible number of items, right, over, we had n minus r factorial. Now we're going to divide by something even more. We're going to divide out all of the combinations that really are the same. In other words, if I have 5 letters, A, B, C, D, and E, and I'm putting them in combinations of 3, would A, B, C be different than C, B, A?
No.
Now with permutations, are those two things two unique permutations?
Yes.
Yes, but now we're having to get rid of all of these duplicate combinations basically and say there's only one group that includes A, B, C. Even though there are a lot of ways you could arrange A, B, C. And the way that we get rid of all those extra arrangements, those permutations, is by dividing by r factorial. The number of arrangements in the arrangement. So we have the number of objects, n, and the size of the groupings, r. Our only thing that's new is we're dividing by r factorial and n minus r factorial. How many different pairs of cards can be made from a set of 3 cards? So let's say I have Jack, King, and Queen. How many different pairs of cards could be made? So once again, we could have Jack, Queen, and then Queen, Jack would not be a different pair of cards, whatever. So we could try to list them out, which I call 5th grade style, and there aren't that many cards even in this set, so we probably could just make a list and find the number of combinations. But, well, knowing that, can anybody tell me how many different pairs of cards do you think, Lauren? 3? Who agrees with her? 3? Who thinks you could make more pairs of cards with 3 different cards? How many more could you make, Jake?
9.
So how would you do that? Let's see, if I have Jack, King, Queen, well, I put them out of order. Let's put them in order. Jack, Queen, King. Lauren, give me the 3 pairs you think we can make.
Jack, Queen, Jack,
There's your 3. That is the 3 that you could make, right? So what are the other 3 that you're thinking, if you think there's 6?
And then you can do, I said 9. Oh yeah. And you can do the same for Queen. And the same
So tell me, what would you say is the first one for Queen?
Queen, Jack, King.
Okay, wait, Queen, Jack, didn't we already have that here?
Jack, Queen.
The order doesn't matter in combinations. How many combinations of cards? So Lauren's right, there are 3. And that's it. So that's not hard to imagine with just such a limited number, but of course we're going to face questions with larger numbers that we might put into combinations. Okay, so let's start with our formula and let's try making it work. Given this formula, what is the n? The n, everybody say it, 3, 2, and 1. Oh, everybody think for a second since you couldn't say it. The n is, recall, it's the number of items that you have, right? The number of them. And then you're going to make them in the grouping sized r, right? So, can we say it now? N is 3, right? We have 3 factorial, which means r, well, maybe you don't, maybe some of you don't know, but we're arranging them in pairs. So what size is that group if it's a pair? 2. So we should have a 2, as you see we do, right? So now we simply use what we know from the formula, and we have 3 factorial over 2 factorial times 3 minus 2 factorial. So if we expand that, before we expand it, I think I'm reducing the denominator. What is 3 minus 2? And 1 factorial is going to be 1. What else? What other factorial equals 1? 0 factorial. Everybody say it? 0 factorial. It equals 1. That's kind of a tricky concept, isn't it? Okay, so now we're going to expand it. So 3 factorial. Expand that for us. What does that look like, Jake? Good. 3 times 2 times 1. And now we need 2 factorial. Gabe. It's 2, or 2 times 1, you could say. And then 1 factorial, we said, is 1. And so sometimes we kind of ignore the 1s because we have these other factors. But when we look at this now, we're looking for multiplicative inverses, like 1 over 1 equals 1, right? And this 1 doesn't matter too much. 2 over 2 equals 1. And so we're end up with what Lauren thought we would have, which is 3. Okay, so it's always good to see that a combination that we know should be 3 works out well with our formula. And now we can face tougher, more challenging combination questions and use this formula comfortably, hopefully. Okay, why don't we try these? We'll bring somebody up here to show us. Who would like to show us? Okay, the first one, Spencer. And here she goes. She's found 6 factorial in the numerator. And she's now doing 6 factorial in the denominator since n and r are both 6. And then what would 6 minus 6 equal here, Spencer? 0, and 0 factorial equals 1. So we could add another factor of 1. Will that make any difference in our outcome? No. So you said you thought everything is going to be a multiplicative inverse, right? So what does this equal?
0.
Wait a minute. When you cancel, or when you have a multiplicative inverse, it equals 1. So put 1. Okay, so who can tell me what this means in the real world? What does this mean? 6 combination 6. Aiden.
6 items grouped into 6.
Right. So how many different combinations of 6 could you make with a group of 6 items? And the answer is 1. It doesn't matter the order they're in. It's like you have a bag full of 6 different dice or something. And it's 1 combination of 6, and that is it. Okay, so that's why it gave us this value of 1. And now how about this one, where we have 9 items put in combinations of 1? And, okay, Jake, you want to do it? So he has 9 factorial over the 1 factorial, but what about n minus r? Okay, I'm going to just back this part up. Okay, so 1 is a factor, you're right. And then we need, what is n minus r? 8 factorial. So can you show us 8 factorial? Good. Good. And so now when you find your multiplicative inverses where we have all these 1s, right? We have what? 1 over 1, 2 over 2, 3 over 3, 4 over 4, 5 over 5, 6 over 6, 7 over 7, 8 over 8, and 9 over 1. So our answer is? 1. 9 over 1 is? 9. 9 over 1 is? 9. There it is, 9. 9 combos. So those of you who said 9, you were right? And what does that say, equal? Equals 9, okay, we're very good. We're ready to have fun with our assignment. You know, the one tricky thing about this assignment on the second page is, listening? You will have to determine whether you need to use permutation or combination. So when will you use, Stuart, excuse me, sit down. Everyone will complete this sentence. Ready? You are going to use permutation when order matters. When order matters. The beginning of my sentence was you will use permutations when order matters. If the order doesn't matter, like let's say you're making a bouquet, does it matter how you throw the flowers together? No, that's a combination. Okay, so be careful when choosing. Page 200, two-sided, I believe. It is only one-sided. There you go. We're going to try the first one together. It says 8 items in combinations of 4. Why is it not working? Somebody's unplugged me. Okay, so you should have a piece of scratch paper and you should set it up just as it is seen in the formula. So n factorial is the first number, right? R factorial is the second number, r. So 4 factorial. When we plug in n minus r, we have 8 minus 4. Okay, so we have 8 factorial over 4 factorial. And what is 8 minus 4? 4 factorial. So we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 and 4 times 3 times 2 times 1. It's happening twice. So we have this multiplicative inverse here. And 1 is not a factor I'm concerned about right now because we always have a 1 in the denominator, right? I see here 4 times 2 in my denominator. Do you see this? I see 4 times 2. 4 times 2 is 8, so I'm an 8 over an 8. And then I see a 3, so I'm choosing a factor in the numerator that I know 3 can go into, and that factor is 6. So 3 goes into 6 2 times. So now I'm bringing my answer over here, or I'll extend the board. So we have 7 times 2 times 5. 2 times 5 is 10, and 7 times 10 is 70. Okay, so that's what you're doing. You are looking for the common factors, or you are reducing, as I did, 3 into 6. But when I have 4 factorial and 4 factorial, I do not combine them. We saw that, we did not see that anywhere. We never multiply factorials together with their exclamation points attached. We have to write out the factorial. 4 times 3 times 2 times 1 times another 4 times 3 times 2 times 1. We write the whole thing out and look for the common factors in the numerator and denominator. Okay?